Right, so this is lecture 8, end of this for week 4. And today, end of this today, I'll release quiz 2. So that will be due tomorrow at midnight. So that means you have roughly 24 hours, a little more than 24 hours to take the quiz. Again, it's the same format as quiz 1. It's going to be on lecture 4, 5, 6, and 7. One thing I realized that initially I said that I lost my annotated slide for lecture 6 is actually not. So 5 and 6 annotated um, slides are combined because I kind of connected together without realizing it. So that's why I was not finding it. So you have slides for 4 and 5 and 7, but fifth one has also 6 lectures is 6 slide. Okay, so these are going to be on the quiz. Everything that we covered today is not going to be part of the quiz. Again, it's the same question. You did well in the quiz 1. I hope that you will also do the similar way in quiz 2. Anything on the slide would be relevant for your quiz. Anything that is not on the slides, on handouts, we don't have to worry about. Homework 3 will be released. That's based on some of the questions we covered from the last homework. It's mostly on rainfall, runoff, and rainfall. Office hour next week on Wednesday, regular time. Again, just because I said Wednesday 1 p.m., I know that some of you may have class during that time. You can always email me and meet another time. So it's really not a factor. So I keep coming back to this particular slide just to show you that different portions are graded. I would, again, this individual part is not necessarily relevant exactly for your projects. That's based on how you set it up. But it's very important after week 5, week 6, and everything we have to see your introductions that is written. And you have to see also on week 7 that at least you attempted the method of how you are setting up your sites and all that. So until then, it's pretty flexible based on the type of project. But by now, which is week 4, you should have your outline. At least you should know exactly what the project is about and scope finalized. If you are still deciding which one of them will be meet the TA, send me. Usually I prefer TA to help you out because that he has a lot more time, but doesn't mean that I don't want to. No, he just send me an email any specific time that you want to meet, then I can meet you. But most of the things can be resolved by TA. But don't work on yourself. Now, if you are worried about or if you don't know exactly what to do, you have helps. This is the last class about runoff. You'll estimate runoff volume because that's the critical part of designing BMP or green infrastructures. So that's going to be our, we'll have some examples so that you can solve the homework questions, which will be next homework questions. I also wanted to tell you that now I uploaded handouts that you should read because that will improve your knowledge about, because you are listening to the lectures, all the materials coming from somewhere. So I uploaded some of the PDF. Those are not necessarily, you don't need to read those to do well in the midterms, but at least this will help you for your projects, if specific things that you need to write in your project. So I'm going to share the um, mm, this is the CCLE website. Okay, so you can see that there are handouts. So for instance, week 1, stormwater pollutants. So again, as you see, this is 133 page. It's not like necessarily I want you to read and understand all of them. This is just used as a textbook so that you have enough resource when you, if you want to write any of them for your project. By no mean I expect you to read 133 page to answer a question on midterms. Anything on the slides are enough for your midterms. Okay, but something like, for instance, event mean concentration, that was on the slides, but you don't know really how where to read more information. You see those here. Okay. Same thing, there are other aspect of pollutants, for instance. Let's see. So these are from different books, different chapters. So it's not from one book. For instance, it says here, this is basically a research articles. So I put it here so that you know what different pollutants are, all those, what's the concentration range it should be in the stormwater. So all those things are here. Um, let me keep going forward, and then you see there is another. So for instance here, stormwater monitoring and sampling guide. I said that some stormwater, how long you have to store, how you have to process the samples. So all those are here. Okay. And determine where to collect, all that. So this might be useful when you design your projects. You have a specific site. If you have any kind of sampling plan, this is something you can write as a guidance. So again, these are all helpful for you to know, um, but not necessarily this is everything you need to read for midterms. I just want to make it very clear. If you understand the slides, you have enough information for your midterms exam. Um, Same thing, if you see the week two, different processes, these are, no, I don't want to, these are something you already learned in CEE159. I just put it here just in case you want to write it, learn it different way. So this is mass balance, as you see. This is, we have in the handouts or in the slides, and these are different example questions. And so anything you need is here already. Okay, so it's really, there's nothing new here. You already know those things. I just put it here so that you know where they're coming from. Week three, I think we have hydrology, week 3 and 4. So this is what we are covering right now. So this has everything. So we talk about runoff. This is the pictures for how do you collect rainfall and where those informations are. So this is all given here. So these are the data coming from these handouts. For instance, today we are going to learn. So we learn about 4 different types of zones where the rainfall patterns could be very different. Somewhere it peak early versus somewhere it peak late. This is the USNRC or SCS data. So this is the table that we use to create different kind of runoff using this data. So this is something you are going to use today. Okay, so the data is here. So I'm not taking from somewhere else. So you might see that in the slides that I refer to table 4.5, this is here. Okay, and you'll learn what that means. But these examples are basically what you're going to do in your homework questions. So these questions are already here. Some of the homework questions are very similar to what you see here. So these examples are already given here. So check those examples so that it helps you how to answer those questions. Okay. Again, these are from different books. So these are different portion of these books I already put in the slide. So when you just skim through it, you realize where they are from by just looking at the pictures, because I took those pictures there on those slides. What I explained is already written here. Okay, so I thought you should have those. For instance, we'll go through this one. We went through this one, green up equations, all that. Okay, so and we are going to cover this portion of the chapter 5 now, this method today. So these are all written here. So if you don't understand something on the slides, you will come back here to see those. So these are written here. These graphs you will see in the slides today. Okay, so and also there are two Excel files. You can use those to solve the homework questions. These are basically the data for different times. So um, I'll give you some example. So that I just want you to know that these are all here. Week 4. Okay, so new share. Any question? Okay, so as I said, these lectures that I put it there, I just show you. This is the lectures, the handouts that you should refer to anytime you don't understand what is covered today's class. So we are going to use this method, core number method, to estimate peak runoff. Last class you learned about rational method. Rational method means amount of flow, or the peak flow is depends on the runoff coefficient C. That depends on how much impervious surface, all the other factors. It's a single number, or I A. If the area is, let's say, that means the entire area has one runoff coefficient. But if you have, let's say, 4 different area, and each area has different runoff coefficient, then it becomes Ci or Cj I Aj. So j is different. J equal to 1, 2, 3, 4. All it means that different portion. So that means for you will calculate independently what is the runoff from this, and then add them together. Okay, so that's how it means. This is summations or some symbols. So this is rational method, okay, and this is very simplistic method. It doesn't account for the fact that the runoff coefficient can also change at different time of rainfall. For instance, runoff would be very different if your rain is happening for 3 hours versus 1 hour, because the amount of infiltration decrease with time. So that doesn't is not accounted by rational method. So that's why core number method is more accurate for those conditions, and we'll get to that. Um, so this is why it is important. It's important because a lot of times, for flood management, if you are engineer or scientist in a watershed area, they will ask you to calculate total amount of runoff that can be received in that area and that properties. And so you'll use this method to calculate that amount of or volume of stormwater runoff you may receive for different rainfall events. And nowadays you use modeling, but this the model that Swim or other softwares that use that model is basically, this is the theory. The function is this. So the fundamentals of those models are what we cover. So again, these are important because we wanted to protect the water quality as well as protect our design or infrastructures from flooding and other resources. So we are talking about water quality, quantity here, not quality. Um, so as I said, now the flooding occurs when your peak flow is more than what's your capacity to discharge. So the peak flows are important when you are looking at the single intensity. That's why just taking single intensity is more useful if you are designing something, whether your design will exceed that volume of water or not. For instance, you are designing a dam. All you are looking for is what's the maximum capacity of that dam. Once it exceeds, it fails, right? So that's why it doesn't really matter what kind of rainfall. You are just interested in the peak discharge. So that's the case. You are looking for rational method. You are looking for the flooding aspect of it. But if you are looking for the discharge rate at different times, and how quickly the peak will appear, all the dynamics, then you have to account for the entire distribution of rainfall, not just the 1 inch of rainfall. So that's the case you are using core number, but because it accounts for the entire rainfall events, it's not about that one rainfall intensity. So let's say what is core number? Well, think of core number is a similar concept in if in the rational method. C is proportional to is a proportionally constant, which means that what portion of rainfall is actually runoff. And now what we are saying is, let's write Corb number. Okay, so this is runoff coefficient, and Corb number is also a runoff coefficient. It's just they are different way to express it. But the difference is Corb number account for the not single rainfall intensity, they account for everything. So we'll see that here. And so why Corb number is more useful? So let's see from the this graph. So this graph is just talk about rainfall patterns and the amount of infiltrations occurs during different times of rainfall or infiltration capacity based on the Winam formula, other formula that we covered before. So this is rainfall, this is infiltrations or loss rate. Okay, so and this is total rainfall or precipitations. This just for simplicity, it's as a step function means it assumes that around certain time your rainfall is constant, then it increase, suddenly increase, and then increase, then stay constant for a while, then it decrease. So it doesn't account, it's not like uniform, it's a discrete increase or decrease in rainfall intensity for an interval of time. Because that's the time you are measuring, because you don't really have any data, continuous data. So now that you have this number and you know the loss rate because of infiltrations or abstraction, all the other factors, let's say this is infiltrations. So now what you know from here is that there are two sides of the rainfall. Number one, as you can see, this is the infiltration capacity. That means this is the infiltration depth. If the intensity is less than that, every water that drops here is going to be infiltrating, right? So that's why any times the infiltration or the rainfall is lower than infiltrations, everything, nothing is runoff. That that part of rainfall is lost because everything infiltrated, nothing become runoff. Once the rainfall or the amount incoming is exceeding what is leaving the system because of infiltrations, that's the rainfall, effective rainfall that becomes runoff. So that means I can write that this section and these sections of rainfall is not contributing to runoff because everything is infiltrated. Okay, so that's the whole idea. So that means the only portion that contribute to runoff, if I make a different color, let's say um, this portion. So that means only this portion of rainfall is contributing to the runoff. Contributing to runoff. So that means this is a portion, the volume. If you multiply that depth into the area of the water side or the area of the locations you are, or the region you are covering, you get the volume of runoff. So that PE is the effective precipitation. Its reason is called effective precipitation because that's the amount of precipitation that actually caused runoff. Everything else is lost because of infiltrations. So that's why if you write the mass balance, precipitation is the total amount of rainfall received in this area. That water can be distributed in three different ways. Number one, IA is basically the initial abstractions. This is the amount. Okay, so those part is gone because of because they are below the infiltration rate. That's initially gone. And F F is the amount in the during when there was a rainfall, there is a runoff contributing. Still, there is a some portion of those will you'll have some infiltrations. So that's the part is F. Okay, so this is the part is F. This is IA. This is F, and remaining portion is the actual runoff, which is what I write as effective precipitations. So if you calculate effective precipitation from this mass balance, PE is basically total amount of precipitation minus initial abstraction, because I mean that's equivalent to amount of rainfall that didn't contribute initially to any runoff. So that's IA. That means it's raining, but you are not seeing any flow because things are being absorbed. Once you start showing flow, that's the part is effective precipitations. But then you subtract that continuous infiltrations, which happens during also rainfall that you don't notice. So this is basically the definition of effective precipitations. That's precipitation minus initial abstractions minus amount retained during rainfall. So basically, you use this term to calculate Corb number. Okay, so that's the factors. Again, Corb number is another way to calculate runoff coefficients. And here we assume that the rainfall, the duration of rainfall is not a limitation for runoff, because it means that t equal to the duration is nearly 24 hours. That means the time of concentrations or duration of rainfall. Let's say this is the duration of rainfall, right? Rainfall is greater than Tc. Tc is time of concentrations. Time of concentration is related to peak flow, because that's the time. If your rainfall happens before the or finish before that, the last drop of water rain somewhere didn't receive to a point yet. So that means it never achieved the maximum flow rate at that point. So, but just know that when you account for core number, time of concentration is not a factor. That means it is your rainfall duration is more than time of concentrations. That means it's
Professor,
longer rainfall. Yes.
on the previous slide, that area shaded blue at the end of the rainfall. That wouldn't be included in the initial abstraction, right? Where does that kind of play into the equation at the bottom?
I
Because it
see.
is part of the rainfall, but it is still infiltration.
I see. I think you're right. I should not have written that clearly. So this doesn't contribute, but IA is the initial rainfall. Okay, so everything else is F, part of F after
Got it.
IA.
Okay, that makes sense. Thank you.
Okay, so there are many type of soil. Soil means now based on hydraulic conductivity, so it's a hydrologic soil group. When you say HBCD, that's hydrologic soil group. A means highly conducting, means water will infiltrate very quickly. Infiltration is very high. D means very low. That's a clay soil. So amount of maximum retention, which is S here, um, amount or maximum can be retained at any watershed or the area, depends on these factors. Soil group, land use. For instance, if it's impervious surface, you retain very less water. If it's more vegetation cover, you retain more. Okay, so maximum retention depends on all that factors, and also initial moisture content. If your initial is dry, it retain much more moisture from the rainfall. So the assumption here is that the ratio of actual retention in a rainfall divided by maximum possible retention for that locations is equal to the ratio of effective rainfall to the maximum possible effective rainfall. Um, so that's the basically the assumption, and I wrote that in equation here. Okay, so F is the actual retention, which you already know here. Okay, that's this term. and S is the maximum possible retention. That's something you don't know. That's a characteristic of that water set based on all these different properties. Is equal to effective rainfall divided by maximum possible rainfall that can cause runoff. So that's basically effective rainfall divided by P minus IA, assuming there is no retention. Because after a point, all raindrop is become runoff because there is no retention. Every water pores in the soil is filled. So this infiltration or retention doesn't exist because it's completely saturated and there is no infiltration going on. So that might happen. That's maximum possible retention. In fact, that happens when you have a long duration rainfall because everything is so saturated that there is nowhere for water to go other than just become runoff. So once you have this number, then what we do is, you know, this equation from previous, this is the mass balance equations. That's written here. This is the mass balance equation. Balance equations. Now the only term that you don't know here is F, but you know this F from here. Okay. So if you substitute F equal to PE times S divided by this, you got this. So all I did is substitute F by this value, um, P times S divided by this. And then you just rearrange the equations, you get this value. Okay. So what that means is effective rainfall can be correlated to um, precipitation and initial abstractions and and the and the S value. So what you did is you remove that F term because F term is very difficult to determine. This is F term. That's really difficult to measure because that's you can't measure because they are infiltrated. So that's another way to remove them from equation by substituting with assumption like this. So once you have that number, now why it is important? Because all these things are measurable. Initial abstractions is basically you are having rainfall but no not enough, so you just time it, and if you know the rainfall intensity you can calculate that, what is an initial abstraction. Precipitation is measurable, you are measuring. S is basically retention, um, maximum retention. That's the property of that location, so that something is also determined previously. So if you know this thing, you can calculate effective precipitations. If you know effective precipitation, you know how much runoff you're going to receive. And to make it even more simplified, that initial abstraction is also is related to the maximum retention. So that initial abstraction is related to land, uh, the type of sites over there. You know what's the how big holes are there, where how much trees are there, and all that factors. So that's why what you can do is you can say that initial abstractions, and you can assume for most of the cases, the in particular in this formula, IA equal to 0.2 S, or another thing way to say is 20% of the maximum retention would be initial abstractions. So that's something is assumption. Okay, this is the assumption. That's for normal. But if you're looking for industrial area or urbanized area, you will not have that much retention. So in that case, this is normally, but for urbanized area, initial abstraction will be very small. So that means this could be maybe let's say 0.1 s or smaller. Or what you are saying is total maximum amount that can retain is only 10% of them will be initial abstraction in urbanized area because everything is impervious surface. There is no place to actually hold them. There are not enough tree. So again, these are assumptions. So let's say you assume 0.2 s. If you do that one, this equation turn into this value. So now what you are doing is you basically don't have to even measure initial abstraction. That's something you can assume. If you know the precipitation value and maximum retention uh, in that particular water set, you can calculate effective precipitation, which is basically the amount of runoff that will be created, the volume of runoff that will be generated in that site. So volume of runoff is basically volume equal to precipitation, which is inch depth times area of watershed. Okay, so that's how you calculate. So now what you know from this equation, you got to know the S value, right? So I told you that S value is something you got to have based on that location site properties. So how do you know that one? And that's exactly where the curve number come in to play. So S is related to curve number using these equations. So S equal to 1000 divided by curve number minus 10. S is again maximum retention of water in that locations. So if your curve number increases, your S decreases, which makes sense. If your core number, as I said, is very similar concept as impervious surface or runoff coefficient. More CN, more runoff. And more runoff means less retention. You don't really have enough capacity to retain the rainwater. And so why it is very different from the initial the rational method. As you see over here, the biggest difference is rational methods, the CIA. If you remember this one, this C is independent of rainfall intensity. That means it's saying that the amount of things you can retain in a site or become runoff is independent of what amount of rainfall happens. But you see that in these pictures, that's not true. Some amount of rainfall, like initial amount, it will be lost. You'll never become runoff, but you do not account for that in your rational method. So that's why this method account for that rainfall intensity. That's why if you see x-axis precipitations and the curve number would be based on the curve number, you get very different p value over here. You have to choose different type of curve number. In fact, that curve number would also change based on rainfall intensity. As more and more rainfall happens, the curve number would also increase. Okay, that means more portion of them become runoff because you completely saturate the soil. So read the handout so that you can understand it better. But I hope this is clear enough. So one of the things that you see over here is the soil group. Okay, so the soil group, as I said, A, B, C, D. This is something you got to do it for your site. I remember showing it you before, but if not, let me show you right now how to do this one. So basically, if you know any location in US, you will be able to find what kind of soil group it is. Okay, so let's try that now. Let me go to that website. So what I suggest is I'm going to give you um, in the chat window, I'm going to give you this link for that website so that you can, you all can try on your own right now. So go to this website, again, bookmark it because it's something you'll need for your site. It's also here in the slide, so you don't have to bookmark. You can always come back. So I want you guys to go to this slide and I'm going to click on that, what I said right now, and open up in a new website. So I click on that. It open up a new web page. So I'm going to share that web page with you so that you can see that web page. Okay, so all right, let me. So what we are going to learn now is how to identify what kind of soil group you have in that particular site that you chose. So this is USDA website. Now that's again, it says what is the soil group means, all that. So you can search for those things. What is that soil group means, all that. The link will give you that access. It says what's the way to do it. It has um, the the instructions. So I'm going to show you anyway. So let's see how do I close it. Escape to close. So it says instruction, but again, you click here, this blue color or the green color things that will open up a new website. So this is where it shows the entire US. Okay. So let's see if it shows the entire world or not. No, it doesn't show entire world, but it shows, as you see, this is a, you can go to these different locations. So let's say I'm going to go to address, then you can, let's say this is Westwood, California. So it says something, let's see where it goes. What is this? Is this the Westwood? No, it's somewhere else. Uh, let's see. I'm gonna see where it is. Okay, it is somewhere else. Let's go to Los Angeles area. Um, or let's say state by country. I go to California, but you can do that any location you want. If you, what I suggest is you go to your home state or home place wherever you are from in US, and you can go there and check that one, and you can go all this county. Let's say if you click this one, it's open up the California. Then I know this is San Francisco, Los Angeles will be somewhere here. So let me go there nearby. So I'm just clicking on. So this is 405. So I know this is somewhere going to be Los Angeles. So I'm just clicking more and more closer. Okay. So now we are getting close to UCLA. Okay. So again, you can do that by adding the address. So if you do have zip code and everything, you can do the address too. So let's say 420 Westwood, Los Angeles 90095. Okay, so now we are in the UCLA. Now what I want is I want to really go even closer. Let's say this is where aisle or the housings are. So let me go here, a little bit green space here. And we saw something here. Again, this is Galley Avenue, and this is the area, a little bit green space. So I want to know what kind of soil properties. So what you do is you area of interest, right? That's where you want to go. So this is you on the right click, you see this is called AOI or AOI polygon. So you can either make a square or you can make a polygon. Usually polygons are easier because you can click which location you want to create or survey it. So I'm just creating a polygon so that I know this is the area. Okay, so double click will give you that area map. So now it says that this is the area we are surveying and this is a soil type. Okay, so now if you go to soil map, it says what kind of soil map. So it's give you two number 1211, 1128. That means there are two type of soil. So this has over here on the left side. If you see, it says urban land, anthracite, whatever that number, loamy substratum. If you click that one, it will tell you what that means. Then it gives you all this information. The one you wanted to see is, see, it says slope is 0 to 5%. Then hydrologic soil group, it says C. This is what you're looking for. C means ABCD, and it means also what's the rainfall, what is the hydraulic or what is the infiltration capacity. So let's see. Salinity, all that given, there is somewhere infiltration capacity. So here, as you see, it says moderate high 0.2 to 0.6 inch per hour. Most limiting layer, transmitting layer. So that's the lowest flow rate you can, or the highest flow rate you can achieve in that layer. Anything above is not. So then another thing you can see is what kind of soil types, everything. You see there are a lot of information. So some of them are relevant for you, some of them are not, but at least you know what to find out from here. So again, if you go to the other corner, click on that, it gives you some other informations. Okay, so hydrologic soil group is B. B means it's little more infiltrations. And as you see, this is the amount of flow rate is 0.6 to 2 inch per hour or this is a KSAT, saturated hydraulic conductivity. All right, so this is what you are going to do, for any sites you want, any locations. It does have all the different function. You can look for all those sites properties. It says soil properties. Everything will be chemical properties. It says, let's say, calcium carbonate. Um, you can see if there is any data informations there. pH, ecological properties, there is nothing there. Soil report. Um, Not to the scale. Okay, so again, the reason I want you guys to see this one is because you want to, if you have a specific site at any location, I know some of you have, this is the software or this is the website, you will use it to understand the soil type in those areas. And you can go for multiple area, larger area. Okay, any question from that? Okay, so we'll go back to our slides. At least from this one, you understood the way you can interpret this soil group type A, B, C, D. Okay, so the bottom line, A means highly infiltrations, D means low infiltrations. That's just the way to interpret it. And so why it is important? Because core numbers or the value that you are going to calculate can also depends on the soil group type A, B, C, D. It accounts for the different type of soil as well as the what kind of development you have on that site. So this is the different type of development. Okay, so that basically that amount of impervious surface, and that also determine how much runoff it can receive. For instance, let's pick a site, open space. This will could be lawn, park, golf courses, or cemetery, means mostly grass cover less than 50%, more than 50%, or 75%. Let's say good condition open space or grass cover is more than 75%. If your underneath soil is A, that means only 39% of the runoff will become, or the core number will be very small, 39. And if it is that means most of them will only a small fraction will be runoff, which makes sense. If your core number is low, that may be less runoff. And if it is, let's say, soil group is D, means very highly clay soil, low infiltrations, the core number will be very big. That means more portion will be runoff. So once you get the core number, you can go back to the slides. You pick one of those number. You know the rainfall intensity, core number. You can calculate the effective P. So that's all you are doing. You are just calculating effective PE so that you can, or the effective rainfall, so that you can calculate the maximum peak flow. So that's what you are doing to check the flooding. Okay, so this is the table. It's given to you in the handout, so you don't have to worry about it. But this is something you'll use for your homework. Okay, so let's use example. So another thing about core number you have to remember is core number is also dependent on the whether it's a dry climate or wet climate or normal climate. What I show you here is the normal climate. Dry climate has a different portion of the core number will change because the drier climate will soak more water or the absorb more water initially, whereas a wet climate will not do that because soil will be always moist. That's why you have to make some adjustment of the core number. So what you do is if you have normal core number from here for drier climate, you have to put one of those equations. So CN1 is dry. This is dry climate. This is wet climate conversion factor. This is CN2 is normal. CN1 is for dry adjustment. This is for wet adjustment. Again, once you know CN, you put this value here. You know the rainfall intensity that's given in your problems. You'll calculate P. If you calculate P, you know the maximum volume of runoff, which is basically area times PE. Okay. Um, so having said that, let's take a break. But in the break, I want you guys, when you come back from the break, um, I want in during the break or something. Let's read the question so that you can think, and then we go back for break, and you will solve as a group together. Everything is given here just so that you can understand it. So it says that estimate the column number, depth of direct runoff, that is effective PE. So I'm asking what is the CN, what is PE, and direct runoff volume means volume is PE times area. Okay. Um, Runoff volume for a 400 hectare drainage basin. So the area is already given. Area is given 400 hectare. Um, if the total depth of precipitation is 127 cm, so that means actual precipitation is 127 millimeters. All soil in the basins are in hydrologic soil group C. So the soil type equal to C. The proposed land use is 50% detached house of 0.1 hectare lots, 10% townhouse with zero point 0.5 hectare lots, 25% school and parking lot, blah, 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 and 15% of open space, park or other things with a good grass cover. So it's basically saying that your entire soil area of A is divided into different portion. Okay, 50% is something else, then 25% is something else, and then rest of the 25%, then 15% is something else, and 10% is something else. Okay, so that's what is given. Okay, so it says different lot. That means each portion has a different cord number. Okay, so CN, so you have CN, different CN value for different locations. Then you have to calculate effective CN for the entire value. Okay. And it says use an antecedent soil moisture condition of AMC3. AMC3 means this value. It means wet conditions. So now that I explain you the questions, when we come back, we solve it so that you know that how to interpret it and do it. So let's take a break. It's 4:51. We'll come back at 5:51, 10-minute break. Not 5:51, 5:01. Right, so I'll stop there. Okay, so um, before the break, we read the question. We say that okay, these are all given. Now the question is how to, because if you know what is asked is your what's the core number, but if you have 4 different locations, each location has their own core number. So you are going to look for the cumulative or the effective core number, which is basically sum together of all. So how do you add them together? Because each area is different. So that's why you have to we have to make a weighted average of the core number. So the actual core number or effective core number would be whatever the core number of that area times the area divided by total area. So let's say this is I'm just saying J means 1 to J equal to n. So here n equal to 4. That means there are 4 different sections in that entire area. So that means you have curve number for each one, CN1, CN2, CN3, CN4. Okay, so all that means is CN1 times area 1 plus CN2 times area 2 plus CN3 times area 3, CN4 times area 4 divided by A1 plus A2 plus A3 plus A4 or entire area. So you know all this value because each value has given what is the area. The area is given. These areas are given whatever amounts. And the C value would be determined from this value. So it describe what is the C value is, and it also say it is a hydrologic soil group type C. So that means you know that from this table you are only looking for this column. So now you are, for this example, you are only concerned about this column, and then you look for what kind of description of the cover type or hydrology conditions here. So good conditions or different grass, if it's impervious or parking lot, then if it is street and road, what kind of road, all those aspects of residential area. It says, let's say, for instance, it says residential area somewhere. Let's see, um, 10% townhouse with 0.05 hectare lots. So 10% townhouse. So if you should look for townhouse, where is the townhouse? Then you'll see that the lot side is a certain amount. Um, so here the townhouse means residential area, and this is townhouse. Um, and then lot size is given. So based on what is the lot size, which location, what's the uh, I think your is the very lowest one, so that may be this one. So it will be 90. So all these numbers you will get from there, and you can substitute that value. So you'll get CN effective. That's what is written here. Once you know CN effective, that's the normal value. So this is all the area and everything all together. I calculate this. But once you know that CN value, you have to convert that to dry conditions, because it says CN3 or wet conditions, by substituting that number. So this CN effective is CN basically 2. And once you know the CN value, you substitute CN value here, then you get the maximum retention. And IA, you can assume that this is only 20% of the maximum retention is initial abstractions. And that's why you can use this equation to calculate the effective runoff. If you know the effective runoff, you know the total volume. Volume would be P times area of the total area. So whatever that size of the area. So this is how you can calculate. Basically, what you are looking for is the runoff, what is the chord number based on the site properties. And so, for instance, let's say one of your project has a location which has many different types of property. You can see that from Google Map. Some is lawn, some is residential property, some is industrial property. You can basically use this value, use this table to calculate the runoff in that entire area, um, based on these functions.
Professor.
Yeah.
So just to make sure that the step one is calculating the CN2 value, right? And then
Yes.
we use that to find CN3.
Yes.
Okay, cool.
And that's because it is given here now. You don't normally have to do CN3 just because it says that use antecedent soil moisture condition as AMC3. If it doesn't say,
Right,
then you
right.
don't have to change that.
Okay, thank you.
Right. Okay, so and this says about total amount of volume, but it doesn't say anything about what's the peak flow, because peak flow is something related to flooding. So peak discharge is basically, you know, that peak discharge CIA is the same thing, same formula. If you see Q equal to CIA before, I keep going back there because that's very easy to remember. This is a very similar concept here. So I is same as the rainfall, effective rainfall, PE, and area is already given. The only difference here, instead of C, you're writing QU. QU is again similar factors that you can use chord number or other factors to calculate QU. So this QU value is again CF times 10 to the power. This is empirical number. It's not really nothing. 10 to the power K, and the K value is here, C0, C1 times time of concentration. So it's a function of time of concentration. So how long the rain before the rain peak appear. Um, this C0, C1, C2, you can get it from the table coefficient calculated. Again, this is the table handout that I provided, so that you know. We'll solve one example. So that way you can calculate the amount of maximum peak discharge. But sometimes, this is the maximum amount of peak discharge. But if you have some kind of swampy area, or let's say there is an area where water can store, that some amount of water will gone into that area. That means your peak will be smaller than or the lower than the what you expected, because some of them are lost. So that's why you have to account for how much percentage of area is swampy. That's why the actual amount of peak flow will be a fraction of the maximum peak flow, and that FP is the related to what percentage is pond swampy area. So that's basically written here. If your 20% is swampy area, that means 3% of the total peak will be lost because of that. So the effective peak will be 97% of that. So this is just the empirical way to calculate the value. Um, so these example questions, I want you guys to solve on your own. I solve it. But no, this is something I want you guys to solve and ask me on campus where. Or if you have time, we'll do it here. But you will do it. I'll just watch you guys doing it and answer any question you may have. So it's the exact same question. Okay, so whatever we did together here, this is the same question. You do this the part one first, and then you use the second part, just this equation to calculate peak. So this is a combination. So it's really not a new questions, because as you see, the second part, it says the calculate the peak concentrations, and these K values are given, all that. Actually, the answer is there. I didn't even realize. So this is solution. So you can see the example. Okay, so now that you learned that all the other factors, one of the things you have to do is you have to calculate peak. So as you see from here, or even Q equal to CIA, all these factors, there is a precipitation that's 127 mm. So that's a constant precipitation. It doesn't tell anything about how the precipitation change with time. What if your rainfall is not one unique depth? It's just increasing, decreasing, which is the case all the time. How do you calculate the peak and runoff everything? Because things will change. As the rainfall goes up, runoff goes up. As it goes down, so everything will change accordingly. So you got to create this runoff or discharge hydrograph based on different types or intensity of rainfall. For that, to solve that kind of problems, you got to understand how to use unit hydrograph concept to solve it. So that's what we are going to solve now. Okay, so that's the unit hydrograph concentration. Again, to reiterate, unit hydrograph means any hydrograph that is because of a 1 inch of rainfall or 1 centimeter or 1 millimeter, whatever that unit rainfall is. So in response to that unit inch of rainfall, okay, or depth of the rainfall is unit, 1 unit. It assumes that the runoff produced in an area is proportional to the runoff durations and intensity. It calculates from effective rainfall amount. So let's see. Once you see this one, you'll understand it. So the very first thing is you'll see this kind of rainfall. So your goal is to calculate the response or runoff based on this rainfall. As you see, these are different rainfall intensity. So these eyes are very different for each different durations. So each imagine nothing happened, only that rainfall happened, only this one. There is a response for that. If before that, there is another response for that. So all of them combined together become the net response. So your goal is to make that response curve. So what you do first is this is given, the precipitation hydrograph would be given to you. Now your next step is to see which portion of the rainfall is actually a runoff. So what you do is you calculate that chord number method, or let's say this is your infiltration, other things that initially that I covered. So that means the actual amount runoff would be, I just put like this. So that means the only thing that runoff is become like this. Okay. So you put that value here. Okay. So you subtract it. So that means this portion not contributing to runoff. So you subtract that, the remaining portion, the hydrograph or effective rainfall hydrograph is this. This is effective rainfall, okay? Once you have this one, then you are going to um, calculate what's the curve would be. Let's say for this one, what is the rainfall curve would be? Something like this. I'm just throwing a number, okay? For the next one, it comes after a little bit after, so this will be like this. Then another one, maybe a bit after, like this. The next one, maybe like this. So this, for each one, there is a different type of discharge curve. When you add them together, this is the final one. This is the sum of all small response or discrete response. Discrete response. So for each one, you have one patterns and then you add them together. So that's the whole idea of a unit hydrograph. So first thing you do is, how do you create the response? You have to first know what is the initial amount. So as you say, remember for last class, we say that there are 4 different regions in the world in US. Each location has different pattern of rainfall. So each rainfall has its own unit hydrograph type. Okay, so that coordinate is given to you. So that pattern that I show you initially. So we'll solve one example, but here is the basic concept. So what it means that now for any for instance, this is a rainfall. This is one rainfall and this is 1 unit inch, 1 inch. Okay, and it rained for certain time. Okay, and I just give a number as delta t. Okay, so that's just the time it rained. Okay, and then in response to the rainfall, you got receive this runoff. This is runoff on the y-axis this side. So you know that the lag time is basically the difference between the center and assuming the peak, the centroid is near to the peak. Okay, so this is the lag time. So that's what we call T lag. T lag is basically the between the center. Here we assume that center is right near the peak. Okay, so that's why TL equal to TP divided by, so you can write here TL equal to TP minus, so basically if you see this is delta T, this is 1/2 of, this one will be delta T divided by 2. Okay, so the TP minus this area delta T by 2 is equal to TL. Just by looking at this equation, oh, it's written here. Um, So if you use this equation, you can basically write time of the peak, time for peak TP equal to, if you take other side, lag time plus 1/2 of your duration of rainfall. That's basically it means here. So what it means that is a time for peak to appear will be lag time plus 1/2 of whatever the rainfall duration you have. Okay, in by chance here I write delta T is the duration of curve. And for this particular method, there are certain assumptions you can make. The rainfall amount or the duration would be 13% of the time of concentrations or 22% of lag time. These are something you can make assumption. Okay, so this is just know this number. This is something based on multiple data point. They give you some way to correlate. Okay. All right. So now that you know, for every rainfall pattern, this is something given to you. So if T equal to T by T peak, TP is the time to peak, okay? Time to for the peak appear. If you, so that T by TP is related to Q over QP, means now what is the discharge in reference to Q over maximum peak discharge. So these number are fixed. Okay, so all you are going to do is, if you know the TP value, T over TP value, you can calculate corresponding Q over QP value, because these are given. This is given. This one you will determine, because TP for your case will be very different based on what water said. So once you know the TP value, so your goal is your your T, you decide now what's the time interval would be. TP you will calculate. Okay, so you will calculate that. That means T by TP you can estimate. If you know the T by TP, you can get Q over QP. This is from table, and these there are four different tables for different type of regions, and that's something the Excel file that I share, that's exactly the value, T by TP and Q by QP value for different region. Once you know this one, all you have to do is you'll calculate Q will be QP times this value. So if you are calculating this number you are getting from tables, if you multiply that times by QP, because you already know the QP value from your location, because TP you can calculate, QP also you can calculate. That's something you already learned how to calculate QP or the peak discharge just few minutes ago. That's QP. Okay. So once you know the QP, you multiply that, you get different Q value. So if you get different Q value, you can basically what you are doing is you plot Q over T. T is given to you and you just get the Q value. And then that's response to one rainfall. Let's say this is the rainfall and this is the response. The next rainfall is like this much. Then it start from here, so the discharge will be like, let's say like this. Then I ask you what is the net for those together, what's the response curve would be. So you just add them together up to here. Then things are adding up here. Then this plus this would goes to all the here. Then this go to like decrease. Then this to this plus this would be another amount. So it's like, this is a combination of that. So that's the whole idea, okay, how to create runoff curve. So let me show you example, because that's the last examples you'll solve for your class or this exam, the homework. So again, QP value is again another formula just to show that how you can calculate. I'll not go through that. So let's say this is example, okay? Because one of the homework question is very similar to these questions. It says develop a synthetic unit hydrograph for a 1.5 mile square mile drainage basin in Memphis, Tennessee, having a time of concentration of 90 minutes. So TC is 90 minutes. Area is 1.5 square mile. And it says, assume that the basin slope are moderate so that the factor 484 can be applied to compute QP. So 484, no, so that's 485 factor is here, okay? So that's number here, 584. So that means it's saying that use these equations. So now, if you see how to solve this one, your unit hydrograph, because Memphis area, you go back, what type of region it is, type 1, type A, or type 1, or type 2, or type 3, or type 2A, or 2B, look for that. Once you look for that, this value is given in your Excel file. Okay, that's in it's in your CCL, you can check that, but I put it here. So this number is here given. So now your goal is to find the TP value. And so what you do is you can decide delta T here is not duration. This is basically what is the difference between when you plot this graph, what is the duration between two interval you should set. So that's equal to 1.003 TC. So that would be PC is 90 minutes. So this is 0.133 times 90 minutes, which will be I calculate before this one, so it's around 12 minutes. So it says that your interval when you do this rainfall hydrograph, it should be 10 at least 12 minutes or lower. If it is higher, that means you are discounting counting those. It become too discrete. If it is less than 10, it will be more accurate, or less than 12 minutes. So that's why in this curve we put 10 minutes, or that example it put 10 minutes. So 0, 10, 20. So you are basically saying that I'm going to plot this graph from 0 to all the way to 27, 270 or 280 minutes. So that will be 6 hour. It is 6 hour or 6, 7 hour. It can go to 24 hours. You can continue because that number is given for. The reason it stopped here is because I see one number becomes zero. Once the runoff becomes zero, you don't want to continue because there is no runoff, right? So um, you basically have this number t by tp. Um, your is t value, and then tp you have to calculate, which is given here. So if you divide 0 divided by 90, it becomes 0. 10 divided by 90, it becomes 0.17. Okay, so here tp is 90 minutes. So this is you calculate. This value you got to interpolate. So as I said, here 0 value, if your t by tp is 0, this is 0. So you put it here. 0.1, it becomes 0.03. For your next one, t by tp is not 0.1, it's 0.17. But here it's 0, the value for 0.1 and 0.2. That means 0.17 will be in between those two values. So either it will be something between 0.03 and 0.10. So that's why you have to interpolate, linearly interpolate, so that becomes 0.17. So this is basically, I'm just going to write this one, not this one. Um, this is 0.17. For 0.17, it will be something like this value. So this value is interpolated from here. Okay, because your TP value is no. From this TP value, you can calculate what if the TP value was 0.17. What should be the Q by QP? Once you know this value, you already know your QP value here. You multiply that, you get your Q value. And so that's how you can plot T versus Q. Okay, so that's what you are trying to do. Time versus flow rate. If you do that for one rainfall, you can do that for multiple type of rainfall. Like here, this is one rainfall, this is second rainfall, this is third rainfall. And then for each rainfall, you get a T over Q value. And then you add them together. So that's written here for this is first rainfall, this is the value. This is the second rainfall, third rainfall, fourth, fifth, all that. And then it add them together. So I suggest you guys to try first before I do anything. That way you learn. I just gave you the example question. This is the homework questions. So I want you guys to think about these two homework questions because this is in the part of your homework 3. So what we do from now on is we'll break into two groups. And so this is a homework question again. And we'll make two groups and you guys going to brainstorm on these two questions. And then we'll discuss that. Other than that, this class is over. Okay, so you can stay around to discuss the homework, but I'll stop recording because we'll have two different groups and we'll try to solve those two questions from homework. So stop recording.